Hello, we're going to look at this two builders, one ladder problem. We're going to follow the maths and see where it takes us. The conclusion is quite interesting. So I've got two builders, Joseph, 75 kilos, Lucy, 55 kilos. The ladder is 10 kilos. We're going to take a mu value, a friction of 0.7 from the floor to the ladder. And we're going to take a frictionless wall. You can imagine there are some wheels up here at the ladder at the top here. And there's another problem where it isn't frictionless at the wall, and we'll look at that another time. Okay, so Joseph and Lucy want to climb this ladder, and they discuss what they should do, and they decide Lucy should climb it because she's lighter. Okay, seems like a good idea. So let's see that. Let's see what happens if Lucy climbs the ladder. Can she get to the top safely? We're going to assume that she gets to the top safely. We're just going to calculate the theta, which gives us. Notice I didn't give the length of the ladder because I hope you can see the length of the ladder is going to just scale this problem up. So actually the length shouldn't matter. Okay, so let's put Lucy at the top. Lucy at the top here, she is going to be 55G. I do need a dimension for this, so I'm just going to call this L. Let's call this 2L. And the mass of the ladder is 10. Have we got everything? We've got reaction force here. Well, this reaction is going to be 65 G, isn't it? And we've got some friction holding the ladder from sliding out. And we know that that is 0.7 times 65 G. Okay, so we've got everything. The ladder's going to move to the right, so there's something missing. We've got a force going this way. And that's also 0.7 65G. And what are we solving for? We're solving for theta. So vertical equilibrium we've used that. Horizontal we've used that. We need to take moments. Notice we couldn't have avoided friction. Okay, friction is acting this way, and that gives us the horizontal reaction at the wall. Okay, wherever you take moments, you're going to have to include moments because these two are a couple. Okay, they're parallel but not collinear. So where should we take moments? Let's have moments down here, shall we? It's about the same. Let's call this point A. Moments at A. So what do we have? Clockwise equals anti-clockwise. Clockwise I've got 10G. L cos. I've also got 55G. 2L cos. That's equal to 0.7 65G 2L sine. Okay, you turn the handle on this, so you calculate theta. So you've got 10GL over here. 10 plus 111 is 120. What do we have over here? Uh, 65 times 2 is 65 times 2 is 130. 130 times 0.7. 91. GL cancels as expected because we knew L would cancel. So divide that through. Tan theta is equal to 120 divided by 91, which is 1.32, well, 1 and a bit. Shift hand, (52.8 to 1 dp). Okay. So this diagram is actually not too bad. So Lucy gets to the top. If we did this in real life, okay, you would have the ladder much closer. 51 is a huge angle. It's quite a small angle. You'd expect a bigger feeder. But that goes to show there's a lot of friction at the bottom. Lucy gets to the top. And then she says, oh, this feels quite stable up here. Joseph, why don't you have a go? So Joseph sits down and does the calculation. And he adapts the calculation, and he realizes he could go to the top. What happens? Well, if this was now 75, this would then be 85, so an extra 20 here. So what we could do is add 20g, which means the friction is bigger, and so this reaction is bigger. Mass of the ladder stays the same. If you do that over here, you'll realize which ones get bigger. Well, that stays the same. And then 55g, this gets bigger. This gets bigger. Okay. And let's demonstrate actually what happens. So you know I'm not faking this. So this becomes 75g. This becomes 85g. Well, what happens down here? Well, this would be 75 times 2, 150. This would be 160g. And this one would be 0.7 times 85 times 2, which is 119g. And you do the same thing again, 160 divided by. You get the 1.34. Shift turn that. So we get 53.34 to 1 dp. And you think, okay, well, that makes more sense. That makes sense because if I put a heavier person, I need my ladder to be steeper, okay, closer to the wall, and so it's not going to fall over. Well, actually, that doesn't actually show the whole story. If you imagine putting an even heavier person on there, or a heavier and heavier person, what happens? Well, these terms start to dominate, the terms that are changing. Okay, you could actually disregard this term because that becomes insignificantly small, and then you can see what happens. Well, then I'll just have m 2l cos theta is equal to mu m 2l sine theta. Okay, this is looking very familiar. Yes, you will eventually get to something like this, where mu is equal to, so if we divide this through carefully, tan theta equals 1. Okay, so we've set it up so that theta is in the wrong place here. So if this is theta, when you shift tan it, you'll get this one here. Okay, right. So if you solve for theta as in the way we've set it up, shift tan 0.7. Sorry, 1 divided by 0.7, shift tan. You'll get 55.001 degrees if you don't want to round down. So around 55 to the nearest degree. So it means that if Lucy was up the top of the ladder and we've set the ladder up at 55 degrees, and says, oh, Joseph, I've forgotten something, can you come up and bring it up here? Yeah, Joseph could safely walk up the ladder, and in fact, you could keep having more and more people walk up the ladder. Okay, what would happen? Well, the mass would keep increasing, but so would the reaction, the friction, because the bigger the weight, the bigger the reaction, the bigger the reaction, the bigger the friction. You could just have, someone that's something that's super heavy up here. As long as one person can get up there, then a load more people can get up there. Okay, especially if you set the problem up with a weightless ladder, or you can calculate the angle first.